about experiment 15.3, which is titled Balanced Forces in a Plane. So there's a little bit of background first. So let's read. It says, suppose that three forces acting on an object are not along the same line, but are in the same plane. So the first thing we have to recognize is the difference between something in a straight line and something in a plane. So we talked yesterday about how if we have an object like a metal washer, and we pull on it this way, and we pull on it this way, and even if we have a second force pulling on it this way, this is forces acting in a line, okay? Now, a plane would be anything two-dimensional. So we could then say, well, what if we added a fourth force, and we pulled on it this way? Then what would be the result of all of those forces acting on the object? And then what if we even added another force going that way? Then what would be the result of all of those forces? Obviously, just by looking at it, we cannot just add these numbers of the forces going at an angle. So if this was 10, and this was, let's say, 6, and this was 4, and this was 8, and this was, I don't know, 15. Okay, just making up numbers. If those were the forces represented by all those vectors, there's really no way to add them numerically or subtract them numerically to come up with the net force. Okay, adding the numbers or subtracting them by making some of them negative like we did with these forces in a line, that works when the forces act in a line. However, as soon as we start looking at forces in a different direction, not in a line, but in a plane, we have to do something completely different to figure out what the result of those forces will be. Okay, and that's what this lab is going to address. So if they are not along the same line, they cannot be added like signed numbers, which is what I just said. We are no longer able to tell whether they are balanced by seeing if the sum is 0. Instead, we must look for another way to combine the forces to find out whether they are balanced. And that is the purpose of this experiment. Okay, now I'm going to give you my version, not out of the book. We'll go back to the book in a few minutes to look at some blue dots and things of that nature. So here's what we would do. And for now, I had to prepare this before I started the recording, so ignore the numbers for now, so that we can focus on what how we would do this lab. So this diagram is meant to give students the line or the direction of the force that they're going to apply. So we take this metal washer, this is the object that our forces are going to be acting on, and we want to hold the metal washer directly over this central point. Now when I had my kids do this, I gave them a big piece of cardboard, and then I took a little push pin and pinned the paper down, and then the push pin served as that central location. So we would take the metal washer, and then we would take 3 spring scales. Now, I don't have 3 hands, obviously, so I am going to lay the spring scales where they would go and explain what we would do with them. So 1 spring scale exactly in line with that line. Another spring scale would be hooked here, and it would be directly in line with that line. And then a 3rd spring scale would be directly in line with this line here. Okay, so then what students would do is we would have 3 students pulling in 3 different directions on this metal washer. And the goal is to keep the metal washer at rest. So everybody's going to be pulling with some amount of force in 3 different directions with the goal of keeping the washer at rest, so it's not moving. And when we say not moving, it needs to be centered over that point where the 3 lines converge right there in the middle. So we'd pull in 3 different directions. And when the students felt comfortable that they were pulling in the exact right direction, exactly along that line, just a little sidebar real quick. When my students did it, I noticed that some of them were concentrating so much on keeping the metal washer still that they'd pull in this direction. So it's really important in this lab that we use the diagram below to ensure that we're pulling exactly along those 3 lines. So the students would pull in 3 directions, staying in line with their, with the correct line. We'd keep this centerpiece still. We keep the metal washer still, completely centered over the central point there in the middle, okay? Now, once we got all of that working and everybody is still and that's good, then we would read their scales and say, okay, well, how much force is this one applying here? How much force is this one applying? And how much force is this one applying? Okay, once we figured out the three forces that were being pulled in different directions, then we can put all this aside. And so then I had my students label the three directions, X, Y, and Z. Let me get this a little closer now for you to see. Okay, maybe a little further. There we go. All right, so we labeled them X, Y, and Z, so we can talk about each of the three directions. And they labeled how many newtons of force they were pulling in three directions. So this person was pulling with 10 newtons of force, this person was pulling with 7.9 newtons of force, and this person was pulling with 6.5 newtons of force in those three different directions. And the result is that the object being pulled on was at rest, okay? Because the object is at rest, I know that these three forces must balance each other. But if you look at the first blue dot question, no, I'm sorry, the second one. The first one says, are all the forces balanced? Yes. How do you know? Because the washer is at rest. Then it says, if you represent the three forces as signed numbers, can you find a combination that will add up to 0? Well, we already discussed back here that when the forces are acting in a plane, let's see, where did it go? Let's see, that we cannot add them like signed numbers. So if they're not along the same line, they can't be added like signed numbers. And if you actually look at the numbers, 7.9, 6.5, and 10, there's no combination. Like if I made this one negative and those two positive, it would not add up to 0. If I made that one negative and added them, no. If I made that one negative, no. If I made these two negative. So if we look at all the different combinations, there's no way to get those to add up to 0. But yet we know if they're balanced, the net force must be 0. So then again, the whole purpose of this lab is to go, okay, so what can we do? How exactly can we add all of these up to find out that the forces are actually balanced? I mean, we know logically that they're balanced because the washer is not moving. But numerically, mathematically, how can we get to that same conclusion? Okay. There's one thing I want to note. We're going to use the word add a few times throughout this lab and then throughout the rest of this chapter. It's kind of important that you recognize we're not always talking about numerically adding numbers like 2 plus 2 is 4. We're going to look at how we can add these two vectors to come up with their combination. But when I say add, I don't mean add 7.9 plus 6.5 and come up with like 14.4 or whatever it is. Okay, I don't mean add in that regard. I mean, if I take this one and I take this one, what would the combination be? What would the result be? And then so if you hear the word add throughout this, we're really looking at not necessarily numerically adding, but looking at what is the combination of those forces. Okay, so here's the first thing we have to do. After we pull on the metal washer and we label the forces in the three directions, we need to come up with a proportionality constant so that we can draw a vector that represents the force. Now, I've already done that, again, because I needed to be a little bit more prepared ahead of time so you didn't have to sit and watch me measure vectors. So what I did is use a proportionality constant of 1 centimeter per newton, which I always like because it's really, really easy. So my proportionality constant is 1 centimeter per newton. So for this 7.9 newton force, my line is 7.9 centimeters long. For this 6.5 newton force, the line is 6.5 centimeters long. And for this 10 newton force, the line is 10 centimeters long. Okay, so when my students did this, I just had them determine what proportionality constant they wanted to use. Some of their numbers were bigger than this because some of them used the 20 newton scales, and so they needed to use something like 0.5 centimeter per newton. And then some of them used really small forces, like they didn't really pull very hard on the washer, and so they maybe used a proportionality constant of 2 centimeters per newton. It really just depends on what your numbers are so that you have a good vector to represent that force, and it's not too long and it's not too short. Okay, so now here's where we're at. Those are the three forces represented by vectors, right? So the 7.9 newtons was going in this direction. There's my arrow. 6.5 going in that direction, and 10 going in that direction. So the next part of the text, which I'm going to paraphrase for you, talks about how can we combine these forces to show, in fact, that they are balanced. Okay, so how can we combine them? And this is where it gets really interesting. There's this method called the parallelogram method. Okay, so what they would have us do, I'm going to start with one that's a little bit more obvious. So we're going to look at just at x and z, and we're going to forget y for just the time being. Okay, if I want to figure out the result of x and z, these two forces, I want to figure out what their combined effect would be. If I'm pulling this way with 7.9 and pulling that way with 10, what direction and with how much force would the object go? I can't add them numerically like we talked about. So there's this method called the parallelogram method that we can use to figure out what the combination of these forces is. So here's what we do. We take a look at the two vectors that we have, and these two vectors here at this corner represent 1/2 of an unfinished parallelogram. So it's our job to take these two sides and complete the parallelogram. Now, a parallelogram, again, I'm definitely not a mathematician, but the way I explain it is, in a parallelogram, opposite sides are equal in length and parallel to each other. So if I'm looking at this and I'm thinking, okay, that's 1/2 of an unfinished parallelogram, I know that the line that starts here going in this direction needs to be equal in length to this one and parallel. So I've already decided that this is a 10 centimeter line because we measured that. So it's a 10 centimeter line. What I like to do, and I don't know that this is mathematically the way you should do it, but it seems logically to work for me at least, is to take my ruler and try to keep it in that same position and slide it up here to where this line ends, to try to keep it parallel, to keep this line parallel to the one that I'm going to draw. And remember, it has to be equal in length. So I'm going to start exactly at the end of this vector here with where the 10 is, because it needs to be 10 centimeters in length. Okay, and it needs to be parallel, so I'm going to try to make sure that my ruler is parallel to the original line so that I draw this correctly. So I'm going to go 10 centimeters this way, and I'm definitely going to use pencil, because if I look at it and I go, it's not parallel. See, it's a little, well, I probably could make that a little bit better. I could probably tilt this side up a little bit and make it a little bit more parallel. It looks pretty good, so I'm going to go with that for now. So now I have 3 sides of my parallelogram. The good news is, after you do the first side, that's the hardest part, because you have to, start at the end, of one of the vectors, equal in length and parallel to the opposite side. Once you do that, all you really need to do then is connect these two sides, because if I did the first side correctly, then this side will automatically be done correctly as well. Okay, so what that should look like to you is a parallelogram. Now, it might not be perfect. It might actually be a little bit off center, but for the purposes of what we're doing, that'll work for now, and keeping the video short so you guys don't have to watch me erase. So I took my two. Again, here's what I'm trying to look at. I want to figure out what is going to be the result of these two forces. If 10 goes this way and 7.9 goes this way, what's the result going to be? So I draw my parallelogram, and then I take the new corner of the parallelogram. I'm recording. Yeah, okay. I take the new corner of the parallelogram, and I draw a line from this corner back to the original point where the object was being pulled on, right here at that center point. Okay, and I draw an arrow, and guess what? That's the result. This vector from here to here, that is the combined effect of this 10 Newton force and this 7.9 Newton force. So if I take this one out of the equation for now and I say, okay, I'm going to pull on an object, 7.9 newtons this way and 10 newtons this way, what's going to happen to it? Well, it's going to go in this direction. Oh my gosh, and guess what? We can figure out the exact force by measuring the line. Remember, we set this up with a proportionality constant of 1 centimeter per newton. So I'm going to measure my line and see how many centimeters it is. and that'll tell me the force. Let's see, it is, well, get out of town. It's pretty close to what it should be. Looks about 6, I'm going to go with 6.5 because that looks pretty good. 6.5 newtons. Okay, so again, we're going to not look at Y for the time being. The whole purpose of the parallelogram method is to say if 7.9 newtons is pulling this way on this object right here and 10 newtons is pulling this way, what is the result going to be? What's going to happen to the object? Well, this object would go 6.5 newtons in that direction. And that's the purpose of the parallelogram method. It's to show you how you can combine two forces that are not acting in a line. Two forces that are acting in a plane. Now, it gets even better. Now, here's what we're going to do next. This is the whole point behind this whole lab, this next part that I'm going to tell you. Well, the first point is introducing the parallelogram method and how you do it. And the second point is this. Now, let's go back and look at all three forces that we originally applied to the object. Okay? So we had an object here. We pulled 7.9 this way, 6.5 this way, and 10 this way. And the forces were balanced. Remember that. We know that they were balanced because we could see that the washer was at rest. So logically we know this. Here's how we're going to prove it mathematically. When there's three forces acting in different directions on an object, the combination of any two forces, okay, so X and Y, and actually let's see, X, Y, Z, let's call this A, just for fun. If we combine X and Z to create vector A, and A is the combination of these two, then A will balance Y. And look at that. When we say balance, equal force, 6.5 and 6.5, in opposite directions. Now we've taken these two vectors and created a third vector from it that's a straight line, in line with that third vector, which shows you that they're balanced. Because remember, two forces that are equal in strength and opposite in direction result in a net force of 0. So the parallelogram method allows us to combine two forces that are in a plane, decide what the resulting force would be, and in this particular lab, when we have three forces acting on an object, the combination of any two will balance the third. So the combination of X and Z balances Y. Remember, this is the combination of X and Z. And notice how it does, in fact, balance Y, 6.5 newtons in the exact opposite direction. Now, the only thing that's a little bit off here, it's not a perfect straight line. And again, I'm human, and this happens sometimes. In a perfect world, this would be a perfect straight line, exactly opposite. So that part didn't work out perfectly, but I was pleasantly surprised, if you didn't notice, to see that the strength of the vectors were exactly equal to each other, which was nice, which is what it should be. Okay. Now what we could also do is do a parallelogram here between these two. Okay, I can measure this line 10 centimeters, and I'm going to do this one quick. I'm going to start at the end of the second line, 10 centimeters in this direction. That's, I don't know that that's perfectly parallel, but it's not too far off. And then I'm going to create the fourth side of my parallelogram. I'm going to go to the corner of my parallelogram and draw a line straight back to the origin of the force right here. Ooh, that one is a straight line. Good girl. Okay, so sometimes when I'm not trying so hard, it works out better. And then we can measure that. So again, the parallelogram allows me to see the combination of Y and Z. So if 6.5 goes this way and 10 goes this way, the result would be a force going in that direction. And if you recall, this force should be equal to this one. So let's see if that worked out. Let's measure it. Well, it's a straight line at least, but it's not perfectly in terms of the force. This says 7.6. So that's pretty close, 7.6 newtons. Okay, we'll call this B. Okay. So again, the combination of any two forces will balance the third when the object is at rest. So three forces pulling on an object. If the object is at rest, then the combination of any two forces will balance the third. And then we could do the same thing here with this one. We could do, this is a 6.5 centimeter, so let's go 6.5. Now this brought up an interesting point when my kids did this. For some reason, these two lines drawing a parallelogram threw them off. Because when you looked at this parallelogram, it's at an angle. And you look at this parallelogram and it's at an angle. This parallelogram is basically a rectangle. And by definition, a rectangle is a parallelogram. But for some reason, my students were kind of thrown off. They were like, I don't even know how to do this parallelogram. And I'm like, well, exactly the way we do the other ones. Opposite lines are equal in length and parallel. Now, just because it turns out to be a rectangle does not mean it's not a parallelogram at the same time, because it is. So we take x and y, we draw the parallelogram, we go to our new corner that we just created, and we draw a line back to the origin. Okay, so there is the combination. X and y will combine to form, let's call it C, just for fun. And if we did this right, this here, force C, should balance this one. Should be 10 newtons, which would be 10 centimeters. Oh, it's a little bit off. It's like 10.2. That's fine. I'm good with that. As long as you recognize they should exactly balance each other. So I can take any two of these vectors, draw a parallelogram to see the combined effect of those two forces. And in this particular lab, here's the whole point. Because the object was at rest, that's the whole qualifying statement behind this. Because the object was at rest, meaning it was being pulled on in three directions, but it was being still. I don't know if that's the right way to say it, but it was remaining still. Let's say that. Being pulled on in three directions, it remained still. So that means any two of those forces, we can combine it to balance the third, and that's what we'll find. Now, if we look in the book, here's the best part of this whole lab, at least in my opinion. It tells you right here. Here's your concluding statement, so you can go back in your book and read through this. It's so nice that they actually pretty much write the conclusion right here for you. It says, what do you conclude about the way forces add? Whenever three forces are balanced, the sum, and again, we don't mean sum in terms of adding it. I mean sum in terms of the combination. And again, my students had some issues with that, so we'll call it the combination. When three forces are balanced, the combination of any two must balance the third. And then it says if they don't balance the third, then the three forces are not balanced. Now in my case, they weren't perfectly balanced in terms of being in the exact opposite direction. And in this case, they weren't completely balanced in terms of being the exact strength, right here and here. But this gives you the method behind how you can combine forces using a parallelogram method. And again, it gives you the conclusion to this whole lab, and the whole point that we were trying to get at is that when three forces are balanced, 1, 2, 3 forces are balanced, the combination of any two must balance the third. So we take x and y and we combine them to form C, which exactly balances that third force. So I probably said that 100 times. It's kind of a little bit complicated sometimes. So I would recommend maybe listening to this a second time just to kind of get a good handle on it. You can practice doing the parallelograms. Number 9 for the REEs gives you some good practice. So again, you're just going to draw lines opposite and equal in length for your parallelogram. Opposite and equal in length. Opposite and equal in length, right? So you can draw the parallelograms and practice figuring out the combination of two forces, right? So if we take these two and draw a parallelogram, the result would be a force going in that direction. And same thing with those. So you can practice a little bit too. And you could actually, on your own, draw any lines that you wanted to, any two forces that start at the same point and go in different directions. And you can practice parallelograms all day if you wanted to, just to kind of get a feel for it. So that you might be more comfortable with it. But that's lab 15.3. And again, the concluding statement is right here in your book on page 311. If you have any questions, please feel free to let me or Miss Kirk know. Thanks for listening.